Okay, for this situation, it's the same as the previous. We have a pendulum at its negative extreme position, -1, not moving, and we apply a unit impulse at t equals 5. Okay, so there's our delta function. So we have we Laplace transform the whole thing, and that's a little sloppy. We apply it to both sides, but I'm just kind of saying we apply it to the whole equation, and I think we understand what that is. So you get s squared L of y plus s, because it's going to be plus the s times y of 0, and then plus, of course, the y prime is 0, but that's 0. Okay, then plus L of y equals e to the negative 5s. This gives you L of y equals e to the negative 5s over s squared plus 1. Plus s over s squared plus 1, but it should be minus s over s squared plus 1. And yep, I really did that. Okay, let's go back to the preceding example for a second. Same as this example, except we apply the unit impulse at t equals 2 pi. Had a plus sy of 0 here, gave us a plus s here. Okay, if you think about it, if you hit the thing at its negative extreme position, it's going to start moving in the positive direction. It's a positive impulse. That all works out, but y prime of 0, oh yeah, that's, never mind. Okay. Brain fog. This should be minus s. I wrote down plus s before. Except, no, hang on. I'm still wrong. If this is plus s, this ought to be minus s. So we ought to have the negative of the cosine function, and that is what it should be. So actually, what I've done is for y equals 1 at t equals 0 in this example. Okay. And there are things that didn't make sense about that. If y was negative 1 at t equals 0, then y should be down here. T equals 0, your cosine should be doing this. And then that changes things a bit. So you can kind of modify that. Okay. You can see how that works out. It matches intuition if it's done correctly. Okay, let's see this one. It's more interesting anyway. Okay, so y of 0 is -1. We apply this. This ought to be a plus s. So this ought to be a minus here. Okay. So L of y is e to the negative 5s over s squared plus 1 half, etc. So that y equals by this shift, you can see this is going to be the sine of t minus 1 over s squared plus 1 would be the sine. This shifts the graph 5 units to the right. So we have sine of t minus 5, u of t minus 5. Then it's going to be minus the cosine of t. Okay, well, that doesn't present a big problem. It's just that you have a different shift here. So if we graph this, using colors as I did before, first of all, your negative cosine of t, which is what should have been used in the preceding, because that would match the conditions. And let's be careful about getting amplitudes right here. So let's just say that 2 pi is here, 4 pi is here, and 5 is about here. Okay, so your cosine, negative cosine of t is going to be down here, and it's going to be up here, and it's going to be back down here. So it's going to look like this, sort of. Now I've made it look like it goes through the point where t equals 5. So I'm going to kind of fudge a little bit and say 5 is here, not here. Okay, so here's the cosine of t. Okay, and it goes through another cycle here. Turned a little too quickly and it's shifted the wrong way. But drawn carefully, you can get the idea. Then the sine of t minus 5, u of t minus 5. The sine of t minus 5 is going to be 0 here. Of course, it would be 0 here, and I'll just use that as a convenient place to start, and it'll be 0 like here. So if I graph a sine, okay, it's going to maximize maybe about here. Going to come up like so, and not going to maximize here, it's going to be 0 here. Got to go through its cycle quicker than that. Okay, going to be 0 here, it's going to maximize about here. Going to be back to 0 here, so it's going to be minimum here. So the first cycle is going to look something like this. And then, so I'm sorry, it's a little hard to draw and get this chalk to turn. Okay, then it's going to do the same thing. It's going to be 0, like here. It's going to minimize here, maximize about here, and here. I'm going to minimize over here. So it's going to come through here. Should have drawn this graph a little higher on the board. Okay, so here's what we have. The story of this pendulum is that we're starting at the negative amplitude, say. And then moving to the right, getting our maximum speed here at equilibrium, and then coming out here to the positive amplitude where it's stationary, then coming back like so. When we hit this thing at t equals 5, what's it doing? Okay? The pendulum, well, y prime is negative here, so the pendulum is moving in the negative direction. We're giving it a positive impulse just a little after it reaches its maximum negative velocity. So it's just past its negative equilibrium, still moving, and we hit it. What happens? Well, my idea is that's probably going to slow it down some. So if we add these two graphs, we see that this one is at a maximum slightly after this one is at a minimum, and it's at a minimum slightly after this is at a maximum, and they're both 0 around the same time. Well, what you're going to end up with is a graph that first of all traces the graph of the cosine all the way up to this point, and then we hit it. And what happens? This is up when this is down. Now, the phase of the cosine is a little ahead of the phase of the sine. So we're going to continue down, but not for long, because pretty soon the sine is going to be as big in the positive direction as the cosine is in the negative direction. So the thing is going to turn around here. Okay? And going to hit 0. The cosine is going to take over. It's going to go through a cycle like something like, well, I'm not drawing it in perfect phase, but we're going to end up with a lot less oscillation. Okay, we've applied a unit impulse to a unit pendulum motion at a time when the velocity is almost, when the momentum, let's say, is almost opposite to that of the impulse. Okay, the impulse is a little bigger in magnitude than the momentum. They're in opposite directions, so the result is going to be a much reduced oscillation. So if you got a pendulum doing this and hit it here, it's going to reduce the oscillation. If we hit it exactly at equilibrium, then we'd have essentially an elastic collision here. The thing would stop. Now, I'm not going through all the physics of it, but just kind of referring to some physics. Okay, so this makes intuitive sense.